Continuing on the lecture for chapter 15 for talking about equilibriums and equilibria, that is. And in this video, we're going to focus on the equilibria for gases. And we'll get into talking a little bit at the end of this video about how to interpret the magnitude of the equilibrium constant. So the equilibria for gases is a little bit different than that for, well, it can be a little different than that for solutions. But the premise is the same, is that equilibria is related to activities. That's the important thing about equilibria. And activities for gases are related to pressures. Right? And so far we've used just a generic K for everything that we've been doing. But when we're focusing on equilibrium for pressures, we use Kp, and P is for pressure. So moving forward, we'll be specifying whether we're doing K for pressure or Kc for concentration. Okay, so pressure will be in either bars or atmospheres. Concentration is always in moles per liter. Right? And we can still talk about gases in terms of moles per liter. That's an easy thing to talk about. We've done that before. So we can still apply Kc to gases, but now we also can apply Kp to gases. And the good thing is that the expression for the equilibrium constant for pressure takes exactly the same form. Okay, so if I have an equation that looks like this, so SO2 gas plus O2 gas with some sulfur trioxide in equilibrium, my expression for pressures will take the same form. It's still products over reactants raised to their stoichiometric coefficients, but now we're talking about partial pressures. So we'll say the partial pressure of SO3 squared over the partial pressure of SO2 squared times the partial pressure of O2 to the first power. Okay, so we're talking about partial pressures of the individual gases. Okay, so this is all well and good, but what if we have information related to concentration and we actually have quite often the need to go back and forth between Kc and Kp. So we have a conversion. So if we need to convert between Kc and Kp, we have an expression, an equation. So Kp equals Kc RT to the delta N power. Okay? So let's talk about what these individual components are. So this is K for pressure, K for concentration. Our R value is related to bars by default. 8.314 bars liters over moles Kelvin. Right? So that means that our temperature needs to be in kelvins. And our N value up here, this delta N, is delta moles of gas. Okay, so the change in moles of gas. If I'm, and this is still, because it's delta, it's still final minus initial. Right? Anytime we see this delta means that we're talking about final minus initial. So in this case, we're talking about product moles of gas minus reactant moles of gas. Okay? So looking back at our equation here, in our reactants, we have 2 moles of SO2, 1 mole of O2, and 2 moles of product. All right, so 2 moles of product, 3 moles of reactants. So if I were to do a conversion on this particular thing, my delta N would be -1. Okay, so let's do a little practice doing conversions between Kp and Kc. And we're also going to tie in some of the things that we did in video 1 with manipulating the value of the equilibrium constant. So we have our equation that we're given. H2S gas, equilibrium with some hydrogen gas and some sulfur gas. Okay, and we're given the value of Kp for this reaction. Kp is 1.2 times 10 to the minus 2. Okay. So given that information, the question is, what is Kc for the following reaction? At 1095 degrees Celsius, so really quite hot. Okay, so we're given the initial information, which is an equation, 2H2S in equilibrium with 2H2 and S2 gas, and we're given the value of Kp for that. And the question wants to know what is Kc for the following equation at a given temperature. Okay, so the easiest way to do this is to first find Kp for the new reaction. All right. So taking a look at our two equations, our new equation is reverse of the original equation. And it's been divided by 2. So it's 1/2 of the original equation. Okay, so in video 1, we learned about what we can do to the value of K depending on what we do to the equation. If I reverse the equation, I take the inverse of K. And if I divide by 2, then I take the square root of K. Okay? So our value of Kp in our given value of Kp, 1.2 times 10 to the minus 2, right? So if I reverse the equation, then I invert K, right? So that value comes out to be 83.3. Right, and if we're being careful with our sig figs, we want to make sure that we track at the second digit. And then if I divide by 2, I take the square root. Which gives us our new value of Kp, 9.13. Okay. So now that I know the new Kp, I can solve for Kc using our conversion equation. So our conversion equation, Kp equals Kc RT delta N. So I'm going to rearrange to solve for Kc equals Kp over RT to the delta N. Now, just as a reminder, make sure you keep those parentheses there, because otherwise you're going to take T to the delta N and you want to take RT to the delta N. Okay? So our moles of gas is the only piece that we're missing at the moment. So we take a look back up here at our equation. So we have 1 mole of H2, we have 1/2 mole of S2, and we have 1 mole of H2S. So delta N is final minus initial, so products minus reactants. So 1 mole minus 1.5 moles gives us a negative 0.5. Right? Then our T needs to be in kelvins. We have 1368 kelvins. Okay, and so now that I have all of the pieces, I've got Kp, I've got R, I've got T, and I've got delta N, I can plug those in and solve for the value of Kc at the new temperature for the new equation. When we do that arithmetic, we come out to a value to the correct sig figs of 0.97. All right, so that particular problem required you to combine concepts from manipulating equations and doing this conversion between Kp and Kc. Okay, this is a really common type of question to be asked. Now, you may be wondering about the value of R, because the gas constant R is notorious for having different values all the time. So the way that you know which value of R to use, by default, we're going to use this value because it's related to bars. Okay? That's not to say that it's always going to be the case. We also have the value that you may be more familiar with from doing ideal gas law problems, which is related to atmospheres. Okay? And what I'm going to tell you is use this one unless the units tell you otherwise. Okay? So if you're given a problem and all of the partial pressures and all the information is in atmospheres, you're going to want to use atmospheres. Okay? But if you're not specified, or even better yet, if it gives you the units in bars, that is sort of a dead giveaway which value of R you're going to use. Okay? But by default, we go with the one that's related to bars. So let's do another practice problem. In this practice problem, we have some graphite, carbon graphite, plus some oxygen in equilibrium with carbon monoxide. And we're given a value of Kc equals 1 times 10 to the 8. So the question is to find Kp at 1200 degrees Kelvin. Right? So this one's a much more straightforward problem. It's not requiring us to manipulate our equation at all. So we can quite simply just plug in some information. Now, I want you to pay attention before we do. That's solid carbon. Okay, that's the same thing that's in your pencil leads. Okay, so that is not going to play into anything involving this conversion. Okay, so when we decide about our moles of gas to put into our equation, that solid carbon is not going to play a part. So our equation, Kp equals Kc RT delta N, and we want to find Kp, so that's easy enough. So so we don't have to rearrange anything here. So our moles of gas, we have 1 mole in our product, and we have half a mole in our reactants. So 1 minus 0.5 gives us a delta N of 0.5. Right, so I can just plug in these values here. Equals 1 times 10 to the 8, 0.08314 times 1200 K to the 0.5 power. So the value of Kp here for this equation is 9.98 to the power of 8, so we can just say 1 to the power of 9. Okay, keeping with sig figs in everything being correct, because we only have one sig fig here in the value for Kc. All right, so the last thing for this particular video is how to interpret the magnitude of the equilibrium constant. Because some equilibrium constants are very, very small numbers, some are very, very large numbers. What do those numbers tell us? Okay, so let's use a couple of examples to begin with. And the first is the best equation in all of chemistry because it results in the production of the best molecule in the universe. And that is the production of water. If you ever take another class with me, or if you've taken class with me before, or know anyone that has, then you know, or we'll find out, that Dr. Lyon's favorite molecule is water. And the value for Kp for this expression, why did I write Kg? That's kind of funny. Kp, 1.4 times 10 to the 83 at 298 Kelvin, so at room temperature. Okay, that's a very, very large value for Kp. Another equation, let's take a look at this one. So solid carbon plus our beloved H2O gives us carbon monoxide plus H2 gas. And Kp for that reaction, 1.6 times 10 to the minus 21 at room temperature. Okay, so much, much different. Big difference between those two numbers, right? 1.4 times 10 to the 83, almost impossibly large value. And then 1.6 times 10 to the minus 21 is a very, very small value. So what do those numbers tell us? So basically, if K is large, so if we say K is greater than 10 to the 10, basically only the forward reaction's happening. Okay, so technically there is an equilibrium. Technically, for this reaction to make water, there is some measurable amount of water that is breaking apart into hydrogen and oxygen at the same rate that water is being formed. But that part of the equilibrium is so minuscule that we say that essentially this reaction goes to completion. Okay, only the forward reaction has any real significance. Okay, if K is large, that means that we're just making water, and an insignificant amount is coming apart in equilibrium. But technically, it is in equilibrium. Okay, so conversely, if K is very small, say if K is less than 10 to the minus 10, only the reverse reactions happen. Okay. So interpreting the magnitude of the equilibrium constant is a fairly normal question. So if if you're given a value of K that is very large, you can say that really only the forward reaction is happening. It's very product favored. It's another thing that we can say about it. And if K is very, very small, we can say that it's reactant favored. Okay. And there's also an important distinction that just occurred to me, that it's at this stage in your chemical understanding, it's important for you to understand that just because we use the terms reactants and products, it doesn't always mean what we start with and what we end with. Okay, it's very, very common for us to think in those terms, starting and ending. But we use those terms in chemistry, especially when we get into understanding equilibrium. We use those terms arbitrarily. By convention, everything on the left side of the equation is called reactants. Everything on the right side of the equation is called products. But it's important at this stage to understand that it's not necessarily starting and ending. Okay? So we're going to stop this video at this point. And we'll continue on talking in the next video about reaction quotients and ice tables.